GADTs, Generalized Algebraic Data Types. Generalized Algebraic Data Types, Ts, are a powerful feature that extend the capabilities of Haskell's type system. They allow you to specify more fine-grained type information for constructors, which enables you to encode additional invariants into the type system and often leads to more type-safe and expressive code. The code block above defines a GADT named expa, representing simple expressions that can either be integers or booleans. Unlike regular algebraic data types, the constructors ival, bval, add, and equal explicitly state which type they return. The eval function takes an expa a and returns a value of type a. Pattern matching ensures that the eval function always returns the correct type for each constructor, effectively making the evaluator type safe. For instance, add constructs an xbar int from two xbar int values, ensuring that you can't accidentally add non-integer expressions. Existential types. In Haskell, existential types allow you to hide the concrete type of a value inside a data structure, providing a way to store different types of data in the same container, as long as they adhere to a certain interface. This is akin to object-oriented languages' ability to store different objects that implement the same interface. In this code snippet, showBox is a data type that can hold any value as long as it implements the show type class, which means it can be turned into a string. This is achieved using existential quantification. The heterolist is a heterogeneous list that contains showBox values of different types, a unit, an integer 5, and a string hello. The main function iterates over heterolist and prints each element using the print function, which uses the show instance of the type contained within each showBox. Phantom types. Phantom types are types that use type parameters without actually using them in the type construction. They are often used to add compile time checks to values without affecting runtime representation. Such types are useful for enforcing additional type safety or embedding more information into the type system. In this code, user ID is a phantom type because it has a type parameter a that does not correspond to any concrete value within the data definition. A is purely at the type level, adding extra type information. Functions create admin ID and create regular user ID create user ID values tagged with different phantom types, admin and regular user, without affecting the underlying int representation. This technique ensures that user IDs meant for administrators and regular users cannot be mixed incorrectly, as the compiler enforces the distinction at the type level. Kind system. In Haskell, the kind system is analogous to the type system, but at a higher level of abstraction. Just as types classify values, kinds classify types. Understanding kinds is essential when working with advanced type features like type constructors, type classes, and especially with extensions like data kinds or polykinds. The code defines a simple data type simple type that has a type parameter a. We then query the kind of simple type and maybe using the type command in GHCI, should be kind or k for kinds. Simple type is a type constructor that takes a type of kind sil and returns a concrete type also star. Similarly, maybe is a type constructor that takes a type and returns a type. In both cases, GHCI will show that simple type and maybe have the kind char, meaning they take one argument of kind, a concrete type, and return a concrete type. Type families. Type families in Haskell are a form of ad hoc polymorphism and can be seen as an extension of the type system that allows you to define families of types that are related by some semantic meaning. They are particularly useful for defining custom type-level functions and can be associated with classes as associated types or exist on their own as standalone type families. In this code snippet, we define a class collection with an associated type family elem. The type elemc is a type function that depends on the type C. For example, for the instance of collection for lists, indicated by a, elem a is defined to be a, meaning that the elements of the collection are of the same type as the list's elements. Empty and insert are methods that operate on a collection. When collection is instantiated for lists, empty is defined as the empty list, and insert is defined as the cons function, which adds an element to the front of a list. Type applications. In Haskell, type applications allow you to explicitly specify the type argument for a polymorphic function. This can be particularly useful with functions that have ambiguous types, or when type inference does not work as expected. To use type applications, Haskell provides the Type Applications language extension, which you enable with a language pragma at the top of your module. In the example, we specify that we want the length function to work over a list of integers. Normally, length is defined for any list with elements of some type a minus int. But by using @int, we tell the compiler explicitly that we want to use the version of length that operates on int. Type applications are written using the symbol, followed by the type you want to apply to the function. Lazy evaluation and Thunk. Lazy evaluation is a key characteristic of Haskell that defers the evaluation of expressions until their values are needed. Thunks are placeholders for these unevaluated expressions. They help Haskell manage memory efficiently and support infinite data structures, among other benefits. In the provided code, infinite ones represents an infinite list of ones, which is possible due to Haskell's lazy evaluation. Normally, creating an infinite structure in a strictly evaluated language would cause a program to run out of memory or hang indefinitely. However, because Haskell is lazy, it only computes what is strictly necessary to achieve a result. The head function only requires the first element of the list, so evaluation stops after the first element is obtained. Thus, when result is printed, it outputs 1 without trying to evaluate the rest of the infinite list. Strictness and laziness. In Haskell, evaluation is lazy by default, which means that expressions are not evaluated until they are needed. This can lead to performance benefits, but sometimes it is necessary to use strict evaluation to avoid memory issues or to enforce the order of evaluation. Understanding strictness and laziness is critical for writing efficient Haskell code. In the code example, sumLazy defines a function that calculates the sum of a list of integers using folder, which is lazy. It will work fine for small lists, but could cause stack overflows with large lists due to the buildup of unevaluated thunks. On the other hand, sumStrict uses foldL, which is the strict version of foldL. It forces evaluation of the accumulator at each step, thereby avoiding the memory issues associated with building large thunks. This makes sumStrict more suitable for large lists. Bang patterns. In Haskell, bang patterns are used to force the evaluation of function arguments. Typically, Haskell uses lazy evaluation, where expressions are not evaluated until their results are needed. However, there are cases when we want to evaluate an argument to a function immediately, to avoid holding on to large data structures or to ensure side effects occur at a specific time. By enabling the bang patterns language extension, we can use in a pattern to indicate that the argument should be evaluated right away. The code defines a function sumSquares, which takes a list of int and returns the sum of the squares of all numbers in the list. It uses a helper function go with an accumulator ac to keep the running total. The bang pattern before ac in the patterns go and go as xxs ensures that ac is evaluated before the function body is executed, which can make the function more memory efficient since it avoids the buildup of thunks, unevaluated expressions, when processing large lists. Exception basics. In Haskell, exceptions can occur at runtime, such as division by 0 or reading from an empty list. Exception handling allows you to deal with these errors gracefully. The primary module for exception handling in Haskell is control.exception. It provides mechanisms to catch and handle synchronous exceptions. Let's explore a simple example of catching an exception. In this code snippet, we import the control.exception module to handle exceptions. The main function uses try to attempt an evaluation of an expression that would cause a divide by 0 exception. The try function wraps the result in an either type, distinguishing between a normal result, right, and an exception, left. We then use a case expression to handle each possibility. If an exception is caught, it's printed to the console, otherwise the result is displayed. SumException is a type that represents any exception. Handling errors with maybe. In Haskell, the maybe type is utilized to represent the possibility of an error in a computation without using exceptions. It encapsulates an optional value. A value of type maybe A either contains a value of type A represented as just A, or it is empty, represented as nothing. By using maybe, functions can safely handle cases that may result in failure without crashing the program. In this example, safeDivide is a function that takes two int values and returns a maybe int. If the second argument is 0, the function returns nothing, indicating an error in division by 0. Otherwise, it returns just the result of the division. This way, safeDivide handles the error case explicitly and safely without throwing runtime exceptions. Using the either type for errors. In Haskell, the either type is commonly used to handle computations that may result in an error. It's a way to represent a value that can be one of two possibilities: a successful result, right, or an error, left. Here's how to use it in practice. The parseInteger function demonstrates how to use either for error handling. It attempts to parse a string as an integer. If successful, it returns right n, where n is the parsed number. If the string is not a valid integer, it returns left, not an integer. The main function shows a simple way to run parseInteger and prints the result. In this case, the string 123 is a valid integer, so write 123 will be printed to the console. Exceptions in I/O. In Haskell, exceptions can be thrown and caught in the I/O context. This is useful for dealing with unpredictable errors during I/O operations. The control.exception module provides functions to work with exceptions in I/O. In the provided code, read file is called to read from a file that does not exist, which will throw an I/O exception. This exception is caught using the try function, which wraps the result in an either type. If an exception is thrown, it will return left and the exception information. If no exception occurs, it returns right with the file content. The case statement then handles the two scenarios. It either prints the exception or the file content. Custom exception types. In Haskell, custom exception types can be created to represent different kinds of errors that can occur in your application. To create custom exceptions, you typically define a new data type that derives from exception class using the control.exception module. In the code snippet, we define a custom exception type called myException with a single constructor, myCustomError, which takes a string to describe the error. It derives from show for printing the exception and typeable to allow runtime type information. We also make myException an instance of exception to use it with the exception handling functions provided by control.exception. The function mayThrowCustomError demonstrates how to throw the custom exception using throw.io when a certain condition flag is met. Understanding monads. In Haskell, monads are a fundamental concept that allow us to work with computations that involve side effects in a pure functional way. A monad is a type that implements the monad type class, which requires the bind and return functions. Monads can model a wide variety of computations, such as I/O operations, state transformations, error handling, and more. Let's explore how the maybe monad works, which is useful for computations that may fail. We define add1 as a function that takes a maybe int and returns a maybe int. The edge operator is the bind operator. It takes a monadic value x and a function val-return val+1, which adds 1 to the internal value if it exists, wrapping it back into a maybe monad with the help of return. We then test add1. With just 1, it produces just 2, and with nothing, it correctly returns nothing, representing a computation that has failed. The I/O monad. In Haskell, effectful operations like input-output O are managed with the I/O monad. Unlike many other programming languages, Haskell requires that side effects are explicitly handled in the type system. The I/O monad wraps these effectful computations and ensures that impure actions do not leak into the pure functional world of Haskell. When a function operates within the I/O monad, it means that the function may perform actions that have effects outside of the function itself. In this code, the main function defines an I/O action. This is recognizable by its type signature, I/O, which signifies that this is an I/O action producing a unit type, indicating no meaningful value is produced. The do block allows sequencing of actions. Put *ln prints a string to the console. GetLine reads a line from the console and binds the result to name. The final put *ln greets the user with the name provided. The Monads syntax within the do block is specific to monads and is used to bind the result of an I/O action to a variable. The maybe monad. In Haskell, the maybe monad encapsulates computations that may fail. A value of type maybe A either contains a value of type A, just A, or it is nothing, indicating failure. The maybe monad provides a way to sequence operations that may fail without having to explicitly check for failure at each step. In the provided code snippet, we define a function safeDiv that performs a safe division operation, returning nothing to signify division by 0. We then create a function chainDivisions that chains two safe division operations using the equals operator, bind operator. This operator applies a function to a maybe value if it's a just, but propagates nothing unchanged. It allows sequencing of safe div calls where any occurrence of nothing will interrupt the computation. Chain divisions is an example of typical usage of the maybe monad to handle errors by short-circuiting computations that might fail. The either monad. In Haskell, the either monad is a way to handle computations that might result in an error. Either a B can either be left A representing an error or right B representing a success. Monads provide a mechanism to chain operations, handling the error case in a uniform way, removing the need to check for errors manually after each step. The code provided illustrates how the either monad can be used to perform a series of computations that may fail. The safeDiv function returns an either string float, where left is used to represent an error with a message, and right contains the successful division result. In chain divisions, we use the do notation to chain division operations. The either monad takes care of propagating left anytime an error occurs, making the function stop at the first error encountered. If all operations succeed, it results in right with the final division result. The state monad. The state monad in Haskell is a construct that allows us to thread state through a series of computations in a functional way. It encapsulates stateful computations by pairing the state with the result of the computation. The state monad is especially useful when you want to avoid explicit state threading through your functions, and is defined in the control.monad.state module. In the code provided, we first import the control.monad.state module. We define a stateful computation called increment, which operates on a state of type int. Using the do notation, we first retrieve the current state using get. We then update the state by adding 1 with put. Finally, we return the initial count before the update. When we run state with the initial state of 0, the output is a tuple where the first element is the result of the computation, the old count, and the second element is the new state. Monad transformations. Monad transformations allow us to stack and manipulate different monads in a single context. This becomes a powerful tool when working with multiple effectful computations. For instance, the maybe monad can be combined with the I/O monad using monad transformers, allowing us to handle both I/O and possible failures within the same block. Here we're going to look at an example that demonstrates this using the maybe t transformer from the transformers package. In the code, maybe t.io indicates that our function is in a context that combines maybe and I/O. We use lift.io to lift I/O actions so they can be used in the maybe context. We then attempt to read a number from the input. If parsing fails nothing, we print an error message and use m0 to represent the failure within maybe t, which encapsulates a maybe action. In case of success, just n, we proceed to print the doubled number. This demonstrates how the monad transformer maybe t allows us to sequence operations that involve both I/O and potential failures as represented by maybe. The reader, writer, and state monads. The reader monad is useful for computations which depend on some shared environment. It allows us to access a read-only shared environment without having to pass it explicitly to every function. In this code, we're defining a simple reader monad operation that accesses the environment to construct a string. The ask function retrieves the environment, which is a string in this case, and we append name to it. The monad laws. In Haskell, monads must obey three fundamental laws to ensure their proper functionality: the left identity, the right identity, and the associativity law. These laws provide the foundation for predictable behavior in monadic operations. The first law, left identity, says that if we take a value, apply the return function to put it into a default context, and then bind it to a function using equals, the result should be the same as if we just applied the function directly. The second law, right identity, states that if we have a monadic value and we use equals to bind it to return, the result is the original monadic value unaltered. Lastly, the associativity law ensures that the order of operations doesn't matter when we chain multiple monadic binds together. Do notation. In Haskell, do notation is a syntactic sugar that allows you to write monadic operations in a sequential style, making it easier to read and write effectful code. It's particularly useful when working with I/O actions, state transformations, or other monadic values. The notation automates the chaining of operations using the bind operator, equals. In this code snippet, main is an I/O action that performs the following steps. 1. Uses put_str_n to prompt the user to enter their name, which is an I/O action that outputs a string to the console. 2. getLine is then used to read a line of input from the console. The that operator within the do block extracts the string result from the I/O action. 3. Another put_str_n outputs a greeting combined with the user's input. Each line in the do block represents an I/O action, and the actions are performed sequentially. Monadic I/O. In Haskell, side effects such as I/O are managed in a pure functional way by using the I/O monad. Actions that produce effects are modeled as values within this monad, allowing for sequential execution that maintains purity. Haskell's runtime takes care of actually performing the effects when the program runs. In this code, main has a type of I/O, indicating it is an I/O action that performs some effect and returns a unit type. Put_str_ln is a function that takes a string and returns an I/O action that, when executed, prints that string to the console. getLine is an I/O action that, when executed, reads a line from the console. The nanit operator is used to extract the result of getLine into name, a pure value within the do block. Finally, we greet the user by constructing a new string and using put_str_ln to output it. What are functors? In Haskell, a functor is a type class that defines how a function can be applied to a value wrapped in a context, like a list, maybe, or other data structures. This concept is critical for working with complex data structures, allowing us to apply functions without having to unwrap and rewrap the data each time. Here, we define the list data structure as an instance of the functor type class, with fmap implemented as the standard map function. This enables us to apply a function to every element in a list. Applicative functors. Applicative functors extend the abilities of functors by allowing for functions that take multiple arguments to be applied within a context, such as a list, maybe, etc. The applicative type class provides the pure function for embedding values in the context, and the /store operator to apply functions within the context. Here is an example using the maybe type. In the provided code, result 1 demonstrates using pure to lift a unary function +3 into the context of maybe, and then applies it to just 10 using the +not operator. Result 2 showcases lifting a binary function plus to work within the same context and applying it to 2 maybe values. Finally, result 3 showcases a combination of functor, concur, and applicative usages where the binary function is partially applied to just 3, resulting in a function within a maybe context, which is then applied to just 10. In all cases, if any of the maybe values were nothing, the result would also be nothing. Monad as an applicative functor. In Haskell, a monad is a type class that provides a way to chain computations together. Since every monad is also an applicative functor, It provides functionality for combining computations, applying functions within a context, as well as sequential execution. The return function lifts a value into the monadic context, while the bind operator sequences actions, passing the result of one as input to the next. This code snippet shows the maybe type as an example of a monad being used as an applicative functor. It defines the applicative instance for maybe using return for pure and a function AP to define the application operator. The AP function uses the monadic bind equals to apply a function within a maybe context to a value within the same context and returns the result as a new maybe. The AP function thus demonstrates how Monad's chaining capability is harnessed to implement the applicative interface. The Applicative Laws. The identity law states that if we apply the pureId function to a value wrapped in a context using for, it should give us the same value in the context. Here, pure lifts the identity function ID into the context of an applicative functor. Applying it to any applicative value v with Thor should yield the same applicative value v. It verifies that the applicative structure does not alter the value inside. MonadPlus and Alternative. The MonadPlus type class is used for monads that also support an associative binary operation with an identity element. In simpler terms, it provides an interface for monads that can also act as monoids. MonadPlus is particularly useful for computations that involve searching, non-determinism, or failure. Let's examine a simple use of MonadPlus with the guard function and the list monad, which is an instance of MonadPlus. In the code, filter even uses the list monad to filter out all odd numbers from a list. The guard checks if x is even. If it is not, the guard function will produce m0, which is an empty list for the list monad, causing that branch of the computation to fail. If x is even, it continues with a singleton list x. The use of the MonadPlus interface allows this filtering with early termination on failure cases. The result of filter even 1, 2, 3, 4, 5 is 2, 4. Lifting. Lifting refers to the process of taking a function that operates on plain values and adapting it so that it can operate on values wrapped in a context, such as a functor or an applicative. In Haskell, this often involves using fmap for functors and lift_a2 for applicatives. In this code, lift_a2 is used to lift the binary function plus to work on values wrapped in the maybe applicative functor. The lifted add function now takes two maybe int values and applies plus to their contained values if both are just variants. If either is nothing, lifted add will return nothing. The purpose of lifting in this context is to allow the direct application of plus to wrapped values without having to manually unpack and repack them. Composing monadic functions. Understanding how to compose monadic functions is essential for writing idiomatic Haskell code. It allows you to chain operations that produce monadic results without getting bogged down in nested structures. Here's a simple example using the maybe monad. This code defines two functions that return maybe values, indicating the possibility of failure. SafeRoot calculates the square root of a non-negative number, and SafeReciprocal calculates the reciprocal of a non-zero number. The equals operator, known as the Kleisli composition operator, is used to compose SafeReciprocal and SafeRoot into a new function SafeRoot reciprocal. This function will calculate the reciprocal of a number and then its square root if both operations are possible. If any of the intermediate steps fail, i.e., the input is negative or 0, the entire computation will result in nothing. Zippers. In Haskell, a zipper is a data structure that allows efficient, purely functional updates to an immutable data structure such as a list or a tree. Each zipper has a focus that can move through the data structure, facilitating updates at the point of focus without having to recreate the entire structure. Here's a simple example using a list zipper. The code defines a list zipper type, representing a focus on an element of a list with context of the elements to the left and right. Two functions are provided to navigate this structure, moveRight and moveLeft, which adjust the focus to the right or left, respectively. If it's not possible to move in the desired direction, e.g. the focus is on the first element and move left is called, the function returns nothing, indicating there are no more elements in that direction.